One. Recordings in progress. Good evening, y'all. This is Code Platoon. What are we? Echo. Evenings, weekends class. This is week 6, day 2. I'm your host, Jordan West. We're doing data structures today. Data structures are another tool in your arsenal. We know about arrays, lists. We know about objects, dictionaries. We're going to talk about a few different other options you have here. Sometimes when you're solving problems, you're going to run into issues with storing data. And real quickly, your lists and dictionaries are not going to cut it in terms of efficiency or space or just accessibility. So we're going to talk about a few different ones today. I just said that. There are other possible data structures besides lists and dictionaries. We're looking at a few common ones today. Stacks, queues, linked lists. As the data structure, each of them has its own characteristics, which makes it either a more or less appropriate tool for solving a given problem. I do like talking about data and organizing data and separating it, putting it around, because your data is going to be the backbone of pretty much everything you do, right? Your UI can handle stuff as efficiently or inefficiently and gather as much crap as it wants to. And you can use as many quick lookup times as you want, but if your data structure does not scale and your data structure doesn't make sense, you're going to be in a world of hurt, and that stuff's hard to migrate sometimes. So we at least want you to get thinking about how you're moving data around, how you're saving it, and this is a good jump into that. We're not going to be doing a lot of asking you to build linked lists in the future, but in some programming languages, it's a little bit more common. Stacks, we deal with all the time. My job is I'm Mr. Stack Trace. When something blows up in the terminal and there's 700 lines, and people say, oh no, it's broken, and they don't read the first line, that's where I come in and read the second line. Stack traces work exactly like you would kind of expect functions to work. They're scoped. They use scope. It's all scoping, right? If I create a function and I call a function within it, and I call a function within it, that function has to complete before this function completes, before this function completes. That's what you want it to do, right? You don't want to start this one, start this one, start this one ends. These die. Orphan processes, zombies, baby. We need to go in and come back the way we came. And that's what a stack is. I'll give 2 more examples just because I've been beaten into my head like this is a hard concept, but I'm going to tell you the other 2. One, you got plates, right? You put this is your first call. It's a plate. Put another plate on top. Put another plate on top. You can't take the bottom plate out without collapsing everything, so you take them off in the order as well. Do we need another example? Sounds good. The next example was crude and involved submarines. So we're not going there. We've seen stacks already. Anytime you run a function, and not because the topical submarine nonsense. I'm not making light of those people that died. I'm making a submariner joke because I'm a submariner. Just so that's out there. Not it's a little too soon for those, or not. I don't care. But I'm not a jerk. Anytime you run a function, you are adding a record to the execution stack, which you can see in the VS Code debugger. I don't use that a lot. I am fine with the terminal, but you can see in the debugger that is helpful and a tool you can use and should use if you enjoy debugging that way. If you try running a recursive function in the debugger, pay attention to how records are added to and removed from the stack. Basically, a function will die and then recall itself. You should find that records are always added to the top of the stack and records are removed from the top of the stack as well. It's called LIFO, last in, first out. Makes sense. Haha, hee hee. This also means that stacks have only one access point, like the unfortunate animals that have to do different things with one thing. This polyp's mouth is also tainous. Stack should, at a minimum, have the following API. Push to add to the top, pop to remove from the top, and peek to return the value of the one on top. That's all. We That's at a minimum, right? We could do more things with the stack, but this is the bare minimum what we're going to do. So let's start with a Python example of what this would look like. So class of stack, init it. We want to build a push, pop, and peek. Push is, that's taken from JavaScript, right? Pushing, we append in Python. Pop, take it off the top, take it off the back. Defaults to the -1 indices. Goodness, Jordan, that vacation was a little too long. And then peek, where we're just going to look at what's at the top indices, or sorry, the last indices. First thing we need to figure out is the underlying data type that we'll be pushing onto and popping off. Most obvious list or choice is a list. There are other options, tuples, or what's the other one? Oh, Jordan, I just had these all loaded up in my brain and didn't leave notes. But if we look at Python data types and ones that are kind of like lists, tuples act like lists. Come on, brain. What else would work here? I mean, we could do a dictionary here if we really wanted to. A map is technically different than a list, but not really. There's a bunch of built-in data types that you don't commonly see in Python. Worth a quick look. 99% of the time you're doing, oh, there it is, range. Range is different than a list for a few different reasons that I'm not a good enough Python developer to get into all the specific reasons, but we do use ranges in Python. They're common. The next step is to implement push and pop. Pretty straightforward using the Python list built-in functions. So since we are saving this as a list, we're going to be able to access list methods, built-in sweep list methods. So kind of as you expect for pushing, when we create the stack, base will be an empty list. We can append whatever item you throw into it and it'll go in there. And it's stuck, it's on the stack. If I push another one on there, it's there, it's in the stack. If I want to pop, if I want to get something off, I have to take the last one. That's my API. You don't get to get the first one. You don't get to get the middle one. If I'm building a stack data type, you're going to have to get it out this way. This is the only way I'm allowing you to take data in and out. So let me go down a little bit further and we'll actually play with this. Finally, we'll need to implement peek. Fairly easy. Peek is just going to return it. So all we did was pop. If you didn't know, this is pseudocode, but pop does default to -1 spot. So if you don't feed pop anything, it takes it off the back. You can give pop indices, take it off. That's fine. Use your manual. And for peeking, we're just going to look at the very top. So very simple stuff. Jordan's stack is going to be, we just instantiate this stack. Why did I do this so long? If we want to add something to it, we are just going to push whatever we want on there. We don't have any rules built into this API yet. I don't look at it and say, that better be an integer. I can put literally whatever I want in there. So running it like that, we can push things onto the stack and then take a look at it. Oh, I need to print this, don't I? There, it's a list with the word foo on it. We can add other things to it. That is how you interact with the stack. I want to get something off of here. I can pop, but it doesn't really take any other arguments. We're not allowed to. It just takes foo. Or sorry, it doesn't just take foo. It just takes a pop. You get the top one off. If I were to print this, I believe pop does return what it picks off. So there, notice when we pop and we print what happens, or we print the return of pop, we do get that back. So pop doesn't just delete it. Pop pulls it off and hands it to you. If you don't want it, that's your, that's your choice. But pop does return whatever it took out of the list. And then lastly, there is print stack.peek. So really shouldn't be looking at this. Method. Why does that not return what I want to see? Oh, no. What's going on here, y'all? Bound method. Oh, I didn't invoke it.
Yeah.
Come on, guys. There we go. So Pete, let's just see the top. Simple data type, right? This data structure. I say data type. I mean data structure. This is simple to understand, right? Does anyone have any questions about what I've done here and what a stack is and how it's working?
So I guess the only difference between peak and pop is just, I guess peak is not removing it; it's just showing it to you. But I feel like
Yeah,
it's still
exactly.
the same thing.
Yeah, pop
Okay.
is removing it. If you look at Python, if you look at Python pop, it's a list method. It takes one off. Because they offered it one, it's going to take banana off. You're left with apple and cherry. If you were to print this, if you were to return, prop does return that method, or sorry, that indices, whatever the value is there. Peak that we've slapped in here is just giving you the value. It's not removing it from the stack.
Okay.
You can decide how you try handling access and empty base. Here I'm just returning none. Yeah, it's probably a good way to do it. Or something more helpful than none, usually. Try catch statements are a real good thing to get into the habit of. And I should leave myself a note to start doing more of those.
So as far as like the stack is concerned, like is there any advantage over using a list besides like we would decide to use a stack if that's just how we wanted it to function? Like we didn't want somebody to be able to remove from the middle, or like our boss said, like I want this as a stack.
Yeah, I mean, that's a way to think about it. You can think about it in terms of how do I want other people to interact with this, and also how do I want to interact with this? Do I want, am I ever going to need to take anything off of this data structure besides the last thing put on there? If not, this is a significantly more efficient than a list. Arrays, in a lot of languages, when you say array, you mean specified list length. You have to say, I'm creating a new array. It's called Jordan's array, and it is going to be, 15 spaces long, and that is all that it can be. It's not going to grow. It's not going to shrink. Why would I do that? It's easier for the computer to remember that. Python does a lot of stuff that makes it real easy for us. Like we say, we want a list, and that means, I can be bigger, it can be smaller, I can add to it, I can remove from it, I can do whatever I want to it. And it's really easy to develop on. It allows developers to do whatever they want. And that's why Python is 200 times slower than C++, because you tell C++, hey, I'm going to make a list. I'm going to call it this. It's only ever going to be this long, and you're going to save it here, please. And then the computer doesn't have to do any of that thought process, because behind the scenes, Python, when you tell it to build a list, it's like, okay, I'm going to build a list and I'm going to call it this, and I'm going to decide that it's going to be roughly this long, but I need to put it in this area where it's not actually set, so I can take it out, remove it, and put it back in there and stuff. And what we're talking about here with these kind of data structures is more efficient ways to build lists. I don't know how quickly we'll get into anything that you need to do these for, but again, as I talked about at the beginning, we want you to know that these things exist. They're common in other languages, and I just kind of want you to at least have an idea of what they are. I can talk a little bit about how linked lists are more efficient than like an array or a Python list. As far as these other two, I have not seen too much of these. This is just the way functions work. You'll see stack traces whenever you're running anything in the terminal. Queues, a little different. I think queues come into where you want things to be, I don't know, where you don't want old stuff laying around. I don't know. I haven't seen queues in use. At least if I have, I haven't realized I've been looking at them. We're going to go over queues real fast. I'm not going to, well, I guess I could rebuild this really quickly. So queues, very similar stacks, except that you insert from the bottom and remove from the top. So it's no longer plates. It's now I don't know, like a tube or something. People walk into one, you wait your turn, and you get out. It's like a turnstile, like a real big turnstile, or like, I don't know. Y'all have any other good? Does anyone not know what
It's like a
I'm
line,
saying?
right?
It is exactly like a line.
Like waiting in any kind of line.
It's like waiting any kind of line. That's how it works. So, queues, you should be able to add an item to the beginning, remove an item from the end, and take a look at the beginning. Big difference here being whatever the last thing you put in the queue is what you're still going to be looking at. So not different than a stack. If we wanted to build that here, what would we? So what is our? I don't want to do too much of this because this is basically what the challenge is. But NQ and DQ, instead of pushing one, I would probably NQ it. And then I wouldn't append. How do you add to the front of a list, y'all? Does anyone remember?
I think insert 0.
Is it insert? Yeah, I think it's insert.
Yeah, I think you're right. Yep. So we could very quickly do that. And then you. I'm not spelling that at all, right? Like, it's all those extras. Like, just stupid. What's this going to be? Pop, what? 0, right? Is that it? Does that make sense to everyone? We're taking off the front, or we're taking off whatever's in the back there. Let's try it out. So I should be able to NQ first, and then second, and then when I do this, I assume oh god. Medicine is fighting for good control right now, y'all. If this works the way I expect it to, then we should be looking at first, right? When that prints, is that right? Is that a oh wait, hold on, we didn't fix it. Off the top of my head, I don't remember. Index and then the number, right? So what's that? Someone speak up. Someone else fix it for me.
I think in insert you got to put a comma after item and give it index 0. Or I don't know if it's the first or the second parameter, but I think it goes last.
Just had it here. I believe it goes first. So we there. Ooh, we got the wrong one. What happened here?
We're printing the return of DQ.
Oh, we are, aren't we?
Because that second is what's coming on.
I don't think you want to insert.
What do we want?
I think you want to put it at the end, not the beginning. So like maybe insert -1.
Oh yeah. Is that looking right? Still not right.
Would you just want append? Could you just append it so it goes to the end?
Yeah, let's try it that way. That makes sense to me. Add it to the end, and then we pop the first. Yeah, that makes sense. And then what is left? It's just the second. That makes sense. All right. We throw it to the back of the line like we said we were. I got off of my head on that. Did I lose anyone there? What we're doing with this queue? When you're adding something on, you put it in the front. And when you're taking something out, it takes from the front. So you continually build backwards and then the front, and they all should shift. Ideally, they should all shift. I don't really have to prove this, but I will just so we see it. Yep, sounds good. Any
I do think you
questions?
had it right first because for the queue, like if they're getting in line, I think you would insert them at the beginning.
Yeah, I think that was it. Where it didn't look. Did I call it quits too early? Was it doing what we wanted to? Am I doing this backwards? What is so look index and then number 0, right? That ought to work.
And then when you pop them, should you be popping them from the end then? So like the first one in comes out first?
I think so. Yeah. All right, cool. 2 ways to do the same thing, but that's how that's totally fine. Good. All right, great. You use insert, you can append, however you want to think about it, whatever makes sense to you, do it that way. We've got a lot of different list methods we can leverage in Python. All right, next, linked list. This is not a complicated concept, but it is complicated to wrap your head around a little bit when you're actually trying to build it out. So a linked list. Let's say I wanted to put all of y'all in a line, and I wanted each and every one of you to not really know anything beyond who you are and who's behind you. That would be a good, efficient way where we can all remember, right? Otherwise, instead of one person saying, hey, I know everyone in line, I know all their names, I know their indices, I don't do that. I just put Philip in front of Corey and then say, hey, Philip, Corey's behind you. And then Corey, Tamiwa is behind you. And Tamiwa, Ken is behind you. And that's all you remember. You just know who you are and who's behind you. And at any point in time, I can say, hey, y'all, make a line, and all you have to do is remember where you are and who's behind you. Or there's no one behind me. That means you're at the end of the line, yeah. So let's see what that looks like. Stacks and queues are both simple data structures. Linked lists, on the other hand, are a bit more complex. Somewhat. A linked list is composed of a sequence of nodes. Nodes have 2 properties, value and reference to the next node in the list. A linked list should have a minimum of the following API: insert and search. So in search, add an item to the beginning or the end, depending on how you want to do it. And then we search, which is going down the list saying, hey, what are you this person? No. Okay. Who do I go to next? Oh, you go talk to him. Okay. Hey, are you this person? No, check with her. It's like, do you know? No, I only know me and her. Like it's very simple data. It's very cheap. It's very easy to build these things out. So let's take a look. Sorry, I am going to check this text message real fast. It's not important. My mom got bit by her lemur, and it's funny. What am I drawing? Okay. She just got back from the doctor. Cool. Node, self-value, next. So this node is going to know, like I said, 2 things. It's going to know its value. It's going to know the next value. Next is a reference to the next node in the linked list, where we default to none, because it won't have a neighbor when it's first created, right? If you're at the end of the list and I say who's behind you, you just kind of, because you don't have one, and that's fine, and that's cheap and easy to remember. But you always know who you are. Now we'll need the basic implementation of linked list class. Insert and search, right? Because we can put one in and we can look. That's what we said we were going to do up here. Since there's only one way to traverse the linked list, you'll need to make sure we have a starting point. And this is what's important. And what maybe makes it a little bit complicated. You do need to keep track of who is the head. So to create the line, it would be very inefficient for me to go to everyone and say, hey, which one of you was number 0? Because I can't just ask, like I have to go to each individual one of you if I don't have a starting point. But if I start with Philip each time, I'll always know, hey, we can start there. That is our, that's our leader. We can at least, find him and move on from there. So when you create a linked list, your first node is going to be set to none. But the very first time you create a node, that one is going to be set to head. It's not going to be changed unless it's deleted or something, but I don't think we're getting too far into that. You would have to rebase your head to something else. We can either create and insert at the beginning or the end of the linked list. Here we'll insert at the beginning. Because of this, we set head to none. Now we'll know we've reached the end of our list when the next node is none. So they're saying we're putting none at the beginning. You start at the end, and we'll know we're done when we get to none. That's fine. You can do it any way you want to do it. We'll create a new node, alternatively insert empty pass an already created node. The new node will become the head node, and the old node will be the new heads next. So what this is talking about is composition, right? We could pass in a node class to insert here, but instead we'll create it here. All the same, I'm going to need to. We're going to remember we still do need this node class. Cool. Cool beans. So we've got our node class, get a value, it knows who's next. In the linked list, we've got a head set to none when you initially create the linked list, and we're going to keep it that way. Sorry, no, we're not. Let me back up. We're going to insert, which will be creating a new node with some value. We're passing in insert value. Old node, which will be whatever was ahead of it. Head becomes this new node we create, and then self head next equals old node. So we're going to be building up off of that. Let's see what that looks like in practice, because that's easy to read and hard to understand. All right. We don't need to build a node. We're going to be creating a node each time we use this insert feature, but we will need to create a new list. So that's linked list. We'll just call it. I can't make up my mind. J list. It's going to be this instantiated list here. And that should be fine. So we're going to insert a new node, and they're going to have values. We can make these values names. Let's insert a name of Philip. Spelling your name right? Sure did not. Did I? There's 2 L's.
Yeah, you were good.
And then let's I want to do that. Yeah, that makes sense. Node object, and the head is going to need a value. Cool. That is our first one. Let's add a new person here. And then Corey, let's see how it builds out from there. So notice our head value has changed. Corey. The linked list is not keeping track of a list at all. Remember when we were doing stack and queue, we were building out this list within. This linked list, this class here is not ever keeping track of anything other than this head. these nodes that are being created do exist. As long as the shell is open, they do exist. Where are they being saved? I don't know. They're being saved right here. They're just classes and they're just chilling out, right? And within those classes, they know their name and their value. So it can be very difficult at first when you're building out this tree, rather this list, and you just want to see the list. You want to see it. You're like I know I'm adding it. Where are these other people? I added 3 people. Where do I have evidence of that? Too bad, so sad. You are gonna have to do it this way. Instead of value, you're gonna have to look at next, right? So, oh, is that why is it doing that? What did I print? Did I say it? What's going on here, y'all? Oh, next
You just
is a
need the
whole-
value.
Yeah,
on
you're
that.
right. Yep, because next, remember, is not their name, it is actually the person. So maybe my example wasn't the best. When I say, hey, Philip, who's behind you? He says, I'll go get him. And goes and grabs Corey and says, this is behind me. And I say, Corey, or who are you? And he says, my name's Corey. Philip doesn't know who Corey is. He knows what he looks like, he thinks. He knows that's your person. Go, that's all Philip really ever has to like keep track of. Linked list doesn't keep track of all that. That's as much as we, know about each other. Wouldn't that be great if that's how we talk to each other? I don't know. Hey, go talk to him for me. No, that's Corey's friend. I don't talk to that guy. Does this make sense, y'all? Am I losing anyone just yet? I'm not
I'm a
teaching
little-
you. Okay, go ahead.
Sorry, I'm a little bit confused at the insert part.
Okay.
Just not sure what's going on there.
All right. This is my chance. Pull up Miro real fast. Up. Second strong. No, that's not. Don't let me sign up. Real quick, I should have probably had this good to go. I don't want to show you all my Miro boards because that's where I keep my D&D campaigns, and I don't want you guys to tell my players what I'm doing. Okay. We'll just find some space over here. All right, here we go. So everyone can see this whiteboard, right? What is a good way to explain this? So when I'm doing this insert function here, I guess I can slap this in here now. When I'm doing this insert function, it needs a node. Either it creates a node itself or I pass in a node. I could update this function to instead accept node, and then rather than inserting a name, I would first like say node is equal to node, and then I'd plug in that node instead. So like that instantiated object, but this node would need things. It's all how you want to do it. Here we're just saying, hey, when insert is invoked, you're going to go create a node. So I've got a linked list, right? Up to this point, JList, I say, hey, this is my linked list here. What happens is we've created a Dropbox. I use this all the time. I can't remember where I draw the dadgum box from. Shapes. All right, so we created a class. This is linked list. This is our class. This is the sweet list that I just made. When I do insert, it creates a node. This is a node, and it is named Philip. and its next is, I don't know. It doesn't know yet. Oh, let me explain this slightly better. The linked list, as we looked at it, it has one thing that it knows. It knows what head is. So we'll say this is head. At first, it's nothing. When I insert, it's a node named Philip, right? When I do that, Philip is going to be, let's say its old node is going to be none. So the old sticky note here, this none that existed before Philip. So now, that is Zoom taking over. This goes on to Neverland, and now Philip is there. In reality, outside of this linked list, if we're just looking at Philip himself, Philip only knows one thing. He knows he's Philip, and he knows his friend is none. If we do insert again, I create a new person. This one is going to be Corey. Our linked list says, okay, I don't know who Philip is. I do know who Corey is, and Corey, in reality, only knows one thing, and it is, this is my friend Philip. And Philip still has none friends. That is what is going on here. So this linked list doesn't know anything other than who its head is, who is in the front. If the linked list is me and I am the teacher, I know who the class leader is, and I say, hey, who's in charge? Oh, it's Corey. Get the class together. Corey doesn't know anybody in the class. Corey has one friend named Philip, but he knows Philip would have a friend this way. And it would this is a bad example because we've got none said here, but let's do one more of it. We're creating a new head. Welcome to the class. You are now in charge, Jesus, and if I need anything done, I know where to start. I start with Jesus, and he goes to Corey, and he goes to Philip, and that's how it builds out. It's called a linked list because it is just a bunch of links. There's not really I can't go and look at my list. I can't look at this and say, hey, who's number 2? Who's number 3? How many people are even in this class? Can I get the person on the front? Can I talk to someone else? Jesus is not being real helpful. Who can I speak to? Too bad. That's not how linked lists work. We start here and we move this direction. So if I were to create a search function, which I'm not doing for you, you're going to figure that out. It's going to have to start here and go that way, right? If I did, but here's the thing, I can still do everything that I want with a list. I'm just going to be a little bit smarter about it. Let's say, all right, we're going to put, no, this list is big enough. So with a linked list, I always have to have my head because that is the only, node I can interact with. I would say, hey, Jesus, you're in charge. Philip is out of the class. Don't want Philip in the class anymore. Jesus says, I don't know who the hell that is. Corey, hey, Philip is no longer part of the class. And Corey says, I don't know who that is. Hey, Guy, Philip is no longer part of the class. And Philip's gonna go, oh, that's me. Leaves class and says, hey, my friend was this is my, this person, pretend like he's me now. So that's how you would make adjustments to the, to the list. You wouldn't be able to go in, pick out what you want to do. You have to very like telephone gamey, go down the list. And that's how information is passed on. And if you're thinking this is really inefficient, this is stupid, it's not. It's very efficient actually, because this is very simple data structure. We're just keeping track of one thing at a time. And it might be faster, to use a list and list methods to blast through this stuff very quickly, but it's not faster for the computer always. Does that explain it any better? Did I make it worse?
No, the visual helps for me.
Okay, great. Because I needed this also. When I sat in as a TA and I had forgotten the linked list structure, and then students were having issues with it. And they said, "Hey, what's going on with this like search thing?" I was like, "Oh yeah, let me take a look at it." And I look at this, I'm like, "Oh, what the hell? What are these nodes?" I don't remember any of this. I was checked out that day. This is how linked lists work. But visualizing kind of how it is now, I would anticipate that you're now able to come up with solutions for things I want you to do. With a linked list, I could ask you to do anything that a normal list would be able to do, but you're gonna have to kind of, come up with a method of accomplishing that. If you're gonna, remove somebody from the middle, your function can't be go find that person and chop them. Your function needs to also include, okay, well, who's behind you? Because now I need to make these people friends if I get rid of their chain. And if you want somebody at the end of the list, there's no quick way to do that. That's too bad. You're going to have to go all the way to the end and say, hey, whoever's at the end, can them. And everyone's just going to have to wait until we get to the end. Any questions about these three data structures? I might have not worded it well when I said, hey, linked list, very simple in concept. It is a simple concept, but don't feel like it should be easy to understand. It is a weird thing to comprehend, like how this data structure, where it's going and what happens to it. But once you kind of start thinking about it as, I don't know, a line of people who only have one friend in their own name, it starts to make a little bit more sense, and you can kind of work through it that way. But with developers, especially new developers, everybody wants to see everything. You want to I want to see the thing I'm building. I want to see all of it, and that's great when you're building stuff this big. But when you're building, something that's processing like billions of entries, like seeing it's not going to help you at all. You need to kind of comprehend where things are going. Not that I am an expert on big data. I'm super not. Even though I've got a sticker that says so. What's up? What's the question?
I don't know if you'll know what exercise I'm talking about, but it was a binary tree exercise with nodes, and it looked really similar. Are those also linked lists, or I guess not, because they each talk to like a left and a right node, and then that node would talk to another left and right node.
So Jordan wants to say, yeah, that's kind of like a linked list. A binary tree is a different data type or data structure. It is very similar to a linked list. It's easy to understand like a linked list. Instead of I know me and I know them, I know me and I know what's there and I know what's there. So you can think of it like that. It's probably a more simplified binary tree. I mean, it is just a straight line instead of a tree. Yeah, I would say it's very similar. It's just a more simple data type or data structure. I would have expected us to do binary tree after this, but whatever. Cool beans. All right, I'm going to stop recording.